Welcome. Good morning, everybody. Glad you can make time for the presentation. So, as Ryan mentioned, I'm the Regional Market Manager for FTI Flow Technology. We're doing this together, and we wanted to give you some considerations for selecting flow measurement instrumentation. The agenda today is to discuss some common flow terms, application considerations for selecting the proper technology, reviewing an application data sheet, special considerations. Then we'll get into reviewing flow measurement principles, theory of operation, benefits and boundaries, and the meter technologies that we'll cover include Coriolis, Vortex, thermal mass, differential pressure, different styles and applications of differential pressure, turbine meters, electromagnetic flow meters, positive displacement, and finally ultrasonic. Common flow terminology. You'll often hear us speak of turndown, which is the ratio of max flow to minimum flow of the meter within its accuracy range. For example, a meter with 101 GPM max flow and 101 turndown has a minimum flow rate of 1 GPM. It's also referred to as the rangeability of the meter. K factor, another common term. This is the number of output pulses per unit volume, so such as pulses per gallon, pulses per liter. Resolution. When we speak of resolution in terms of flow, it's what volume is represented by each pulse. So it's the inverse of the K factor. The K factor is pulses per unit volume. The resolution is volume per unit pulse. It's critical, especially when measuring very low flow rates or very small total volumes, that resolution is fine enough to give you an accurate reading. Other fluid properties under consideration: density, specific gravity, viscosity. Density is the mass per unit volume. For most liquids, it varies with temperature. Specific gravity is the ratio of density to that of water. It's found by dividing the fluid's density by water's density at 60 degrees Fahrenheit. It varies with temperature as well. Viscosity is a measure of a fluid's resistance to shear angular deformation, the resistance to flow. Two versions, absolute and kinematic. And kinematic viscosity is the ratio of absolute to specific gravity. Viscosity varies with temperature as well. You'll hear us talk about accuracy and repeatability. Repeatability is the ability to repeat and hit the same result at the same flow rate over and over. In the top target, obviously, we're not repeatable. We're all over the place. In the bottom left, we're repeatable. We're close to hitting the same mark every time, but we're not accurate. And then finally, accurate and repeatable. When we look at applications, some of the considerations that we take into account to select the right technology is, first of all, the accuracy that's required for the application. The type of process, what purpose are we doing? Are we doing batching? Are we doing leak detection? Are we trying to do control of flow? Then we get into physical characteristics. What fluid's being measured? Do we have suspended solids? Is there chemical compatibility issues? Then we start looking at viscosity at the operating temperature. The wider range in temperature will change the viscosity. We just have to be sure that the meter can handle it and that we calibrate accordingly. Obviously, we need to know the estimated flow range, the operating temperature, the operating pressure. Then we also want to look at installation envelope. Do we have space limitations? Is it going on vehicle? Is it going in a cabinet? Things like that to determine whether we need to maybe have the electronics separate from the flow meter body. Do we require a display? What kind of outputs do we want? And then in the area classification, is it hazardous classified? Are there explosive gases and vapors or dust that we have to be concerned with? And obviously budget. We need to know, we want to make sure that we have a meter that's within the budget constraints of the customer. A typical application data sheet asks these questions. Again, we're looking at the liquid, the description, viscosity, pressures, temperatures, percent solids, flow rate, temperature, pressure, as we saw in the previous slide. The reason we ask this is the applications engineers will use this to understand the fluid. Details on pressure, temperature, suspended solids, flow range, viscosity, and pressure drop. This is how they select the correct technology to measure the fluid. In the other part of the application data sheet, you see things specific to line sizes, material of piping, end fittings, power availability, do you require display? This is used to complete the meter configuration. Do we need electronics? If so, how are we going to mount them, either to the meter or separate? What kind of mount end fittings do we need? And are there any special considerations? We're going to get into meter technology. The first one we'll talk about is Coriolis. It's one of the newer technologies in the marketplace. Typical components of a Coriolis meter is you've got a drive coil and magnet in the center. This is attached to the two tubes, and it actually vibrates them. And then you've got pick-off coils and magnets that pick up the vibrating tube excursions, along with an RTD for temperature measurement, and then your process connections. So the way a Coriolis works is the fluid enters the sensor and is split in half to go through two tubes. The tubes are vibrated in opposition to each other by the drive coil. Remember, it was attached in between the two coils. With no flow, the tubes are oscillated at their natural frequency. Magnet coil assemblies called pickoffs are mounted on the flow tubes. Those are the other two sensors. As each coil moves through the magnetic field of the adjacent magnet, it creates a voltage in the form of a sine wave. So the vibration of that tube causes that pickup coil to vibrate, and we see a sine wave produced from the drive from the pickup coil. During a no-flow condition, there's no Coriolis effect, and the sine waves are in phase with each other. When the fluid's moving through the sensor's tubes, Coriolis forces are induced, causing the flow tubes to twist in opposition to each other. This causes a phase shift in the sine waves, and the delta T is proportional to the mass flow rate. So here we see, with no flow, the sine waves are in phase. With flow, there's a shift. Benefits of Coriolis meters. The measurements are unaffected by fluid density changes. They can accurately measure changing densities. They're very suitable for liquid, gas, and steam. They're currently the highest accuracy. They're suitable for custody transfer. Custody transfer is where you transfer goods under regulation. Fuel, your gas pumps, if you're transferring fuel between customers, validating that what you received is what was sent to you. Multivariable, they can measure mass flow, density, and temperature. They're highly reliable and they're very low maintenance. They're easy installation, no inlet or outlet sections are required. The limits of Coriolis, they're expensive, especially for lines above 2 inch. They have a very large installation footprint because of their design, especially the older U-tube and Omega tube designs. The pressure drop can be quite high for the older U-shaped and Omega tube designs, especially with high viscosity fluids. You have a very limited range of wetted materials that can be used. And they can be very expensive or limited use for corrosive fluids. Again, it just depends on the material that you can make the tubes out of. Typical applications for Coriolis, food and beverage, ingredient measurement, chemical processing, oil and gas processing, and test and measurement. The next technology we'll talk about are Vortex Shedding flow meters. The Vortex Shedding theory is that you've got a non-streamlined object, a bluff body in the path against a flowing stream. So you've got laminar flow on the left, it hits this bluff object in the path, and it creates alternating vortices. So the bluff body causes the fluid to alternately separate from the top and bottom sides. The boundary layer of the fluid becomes attached and cools back on itself, forming vortices. The distance between the vortices is constant depending solely on the size of the bluff body that formed it. Typical process, there's two main design characteristics. The one on the left is a vortex shedding bar. What happens is the flow hits the shedding bar and splits to either side. It causes that shedding bar to oscillate, and there's a sensor that picks up that frequency, and that frequency is proportional to the velocity of flow. On the right illustration, it's similar, but we're using piezoelectric sensors to catch the pressure, the alternating pressure cycles of the fluid. Benefits. It's suitable for liquid, gas, and vapors. There's a variety of installation styles, either inline or insertion probe. They're relatively inexpensive, especially in smaller sizes. Basically no moving parts because the oscillation of the shedding bar is very small. Boundaries, they're not suitable for pulsating flow. You do have the requirement of long inlet and outlet straight run sections. 20 to 30 pipe diameters is typical. You don't want to use these for high viscous fluids or low pressure gases because there's not going to be, in the case of high viscous fluids, it's not going to flow readily around the shedding bar. Low pressure, you're not going to create the vortex shedding effect. You do have a minimum velocity in order to create that vortex shedding effect. So fluids with low velocities are difficult. It's got lower accuracy compared to other technologies, especially at the low flow range. They have limited turndown, and pressure drop may be high because you're restricting the bore with the shedding bar. Applications where vortex meters really shine is in steam measurement. They're used a lot in power generation and utilities where you're delivering steam power generation. They can be used in dirty and wet gas. They are used a lot for airflow, natural gas, water, and DI water. Thermal mass is the next technology that we'll cover. These are gas type meters. These were developed back in 1914 by Vesso King, became the basis of King's Law. Basically, we're talking about a hot wire anemometer. As the air moves over the wire, causes a loss of temperature in the wire and removes some of the wire's heat energy. This heat transfer is proportional to the mass velocity at the point in which the flow is contacting the wires. The way these work is one sensor is an RTD, the reference sensor. It's measuring the gas temperature of the fluid. The flow sensor is heated and maintained at a constant temperature. As the gas flows against it, it causes that heated sensor to lose heat, and the energy that's required to maintain that temperature is proportional to the mass of the flow against that element. So this is just a diagram showing how it works. And again, we're doing two RTDs. One's measuring the flow stream of the gas. The other is heated and acts as a flow sensor. The heat loss is proportional to the mass flow of the gas against that heated element. Then they generally have a transmitter attached to them that linearizes the data and converts it to a process signal, either analog 4 to 20 or Modbus. Benefits and boundaries of thermal mass. They're relatively inexpensive to set up, especially the insertion styles. They're very low pressure drop. They have no moving parts. They do have very wide turndown ranges, and you can do very large lines with them. Limitations to thermal mass, they're easily knocked out of calibration, especially if you have particulates. They're clean gas only. And they are sensitive to the gas composition, so they're calibrated for a specific gas. If you're using methane versus natural gas, it's a different calibration. So you have to be very specific on what gas you're going to measure. Typical applications: compressed air, natural gas, emissions monitoring for stack or flue gas, where you know what the composition is, landfill gas recovery, flare gas, gas leak detection. So a very good broad way to measure gas mass flow. Differential pressure flow meters. There's a multitude of different designs and styles using differential pressure, or DP. The meter on the far left is an integral orifice. So it's got ports on either side of the plate that's put in line, sandwiched between flanges. As it flows through, it creates a differential pressure across the orifice, and then the mounted transmitter to it turns that into a flow rate. In the center is a Venturi. There's a further detailed description in this presentation, as well as the one on the right, which is a two-port tap across the plate. Differential pressure flow meters employ Bernoulli's equation. Bernoulli assumes that your fluid and device meets 4 criteria: that the fluid is incompressible, that it's non-viscous, that you have a steady flow rate, and that the flow is along a streamline. It's not turbulent. Describes the relationship between pressure and velocity of a flow. DP meters guide the flow into a section with different cross-section areas, different pipe diameters, that causes variation in flow velocity and pressure. By measuring changes in the pressure, the flow velocity can then be calculated. This is an orifice plate. It's a plate put in to restrict the flow. You have an upstream and a downstream pressure tap. As the fluid passes across the orifice plate, you get the increased pressure upstream versus downstream. And again, you can calibrate that differential pressure to a flow rate. A Venturi is a different style. It's a section of tube that forms a relatively long, smooth passage with smooth entry and exit. The Venturi tube is connected to the existing pipe and then narrows it down to a small diameter and then opens back up to the existing pipe diameter. This is where we're measuring the differences is across the cone. So the changes in the cross-sectional area cause a change in velocity and pressure of the flow, or we're restricting it. The differential pressure of the unrestricted and restricted flows measured and velocity can be determined. V-cone, again, this is another style of restriction and flow measuring differential pressure. The differential pressure is created by putting a cone in the center of the pipe. The flow rate is calculated by measuring the difference between the upstream pressure and the pressure at the cone. And we know what the restriction is, and so we can calculate velocity and flow. Pitot tubes, these are what you see sticking out of the wings of airplanes to measure airspeed. Pitot tube, it's got a tube with a hole in it. It's inserted into the flow stream. The tip is stationary. Its pressure compared to the static pressure is used to calculate flow velocity. Pitot tubes measure the flow velocity at the point of measurement. On the left-hand side is on the right-hand side is a different style. It's an averaging pitot tube, so it has multiple ports. And so it gives you an average of the flow profile over a range of the pipe. whereas the Pitot tube is only at the point where it's inserted. Differential pressure pros and cons. The benefits, they're suitable for liquid, gas, and steam. They have very large size ranges because a lot of them are insertion style. They can tolerate extreme process conditions. It's totally dependent on the pressure transducer or pressure transmitter that you use. The transmitter can be replaced without shutting down the process, and they're entirely electronic, the transmitters are, with no moving parts. Limitations, you have limited rangeability, typically 3-to-1, top 10-to-1. They're not a very accurate measurement compared to other technologies. Accuracies are generally in the 2 to 5% range. You have long straight run requirements because you don't want turbulence, you want laminar flow. And they're affected by changes in density, pressure, and viscosity, especially on gases. And you cause an unrecoverable pressure drop. Typical applications for DP is air, natural gas, water. You can use clean and dirty fluids. It's all dependent on the transmitter that you have attached to it. Industrial gases are good applications, chemicals, slurries. So yeah, wide rangeability of application with differential pressure. It just depends on the primary measurement element as to which one's suitable for which type of process. Next, we'll talk about turbine flow meters. The theory of operation on a turbine is you've got a free spinning rotor made of ferrous material mounted inside at right angles to the flow. So it's perpendicular to the flow. The rotor is suspended by 2 end supports, which act to straighten the flow prior to reaching the turbine rotor. As the flow reaches the turbine begins to spin due to the applied force by the flow. It goes against that blade. The blades are at a pitch and it starts to spin like a propeller. The rotation of the rotor is proportional to the rate of flow. The pickoff sensor actually creates a field, either magnetic or RF. And what happens is as that rotor blade passes through that field, the pickoff sensor creates a pulse. The pulse is generated by the pickoff operated frequency that correlates to the velocity of the fluid. So we have a mechanical design. We push against the rotor interrupts the magnetic field or RF field of the pickoff. We create a frequency output. Why do we use precision turbines? Accuracy is the big one. 0.12% of reading is achievable. Calibration accuracy, 0.05%. Linearity is very high. Repeatability is very high. Typically, high turndown, 100-to-1. They have a very small footprint when compared to other metering technologies. High resolution, we can use these for leak detection. So typically a 4-6, which is a 1/4 inch meter, 48,000 pulses per gallon. Our low flow design, we get 800,000 pulses per gallon. So very high resolution. High speed, typically a millisecond or better response to a change in velocity. They are rugged. We have designs that we use in hydraulics, high shock. And they're pretty cost effective when compared to other technologies. And we talked about repeatability and turndown. Repeatability is what we do on the turbines. The way we're able to hit high repeatability and turndown is by reducing drag on the rotor blade. So the bearings are very precision, the rotor is very precision. So we just do everything we can to reduce drag on that rotor, let it freely spin. Meter construction, 2 basic types: axial, which is the one we discussed before with the rotor perpendicular to the flow, and then a tangential construction. This puts a rotor in line with the flow, acts like a paddle wheel. The benefit for the tangential is, again, we have very, very low drag, and we can measure very, very low flow rates on that, down to 0.001 GPM. Benefits, we've discussed high accuracy, repeatability, fast response. They are able to handle very high pressures and temperatures. They're a compact design, and with advanced electronics, we can do temperature compensation of the fluid. We can do mass flow and a variety of outputs. Boundaries are, it is mechanical, so we have moving parts and we have bearings. Bearings will have wear depending on the particulates that you have. They're recommended for clean liquids and gases only. And depending on the corrosivity or the nature of the corrosive fluids, we may not have material compatibility. Applications, again, a lot of the same. Food and beverage, clean in place, reverse osmosis, pharmaceutical, DI water, chemical processing, solvents, gases, oils. They're used where we need high accuracy for batch control. In test and measurement, we do a lot of onboard testing for fuels, hydraulics, transmissions, lubricants, diesel exhaust fluid, a lot of dyno testing and onboard vehicle. We do engine coolant flow, hydraulic systems. Next, we'll get into the electromagnetic flow meters. These operate according to Faraday's law. It's a pretty common technology. So what we do is we create a magnetic field. Faraday's law states that a conductor moving in a magnetic field generates an electromotive force. The formula is E equals KBdV. B is the magnetic field. It's a constant by design. D is the distance between the electrodes. It's held at a constant. V represents the velocity of the fluid, and K is a constant. Therefore, the electromagnetic force is proportional to the velocity. Everything else is constant. The nice thing is these signals are not affected by temperature, pressure, or viscosity changes. Wide range availability from 1/4 inch to 96 inch. A variety of liner materials, so Teflon, plastic, ceramics, a variety of electrodes, stainless, Hastelloy, tantalum, titanium, platinum. So again, to cover the range of chemical compatibility. Installation methods typically are flanged, MPT, tri-clamp, wafer. We also have hose barb. And there is an insertion style. So the bottom here, you hot tap a pipe, you have a ball valve, and you can insert it while the process is running. The transmitter, typically for a magnetic flow meter, is available in AC, DC, or battery power. It gives you 4 to 20 milliamp output, linear frequency or scaled pulse outputs. It's available with Modbus or HART, which are industrial process communication platforms. It'll display rate and total. You have access to menus for scaling, alarms, and that. And the transmitter can either be mounted directly to the flow tube or it can be remote mounted onto a pipe stand. Benefits and boundaries of mag meters. Pro, wide range of affordable materials and construction to measure aggressive acids and chemicals. It's not affected by pressure, temperature, or viscosity changes. It works excellent with entrained solids because it's open bore. There's nothing in the path, so it'll pass right through the meter. Very high accuracy, typically 1/4% of reading. Again, high rangeability from 1/4 to 96 inch and no moving parts. Limitations of mag meters. The fluid has to be conductive, so anything water-based is perfect for a magnetic flow meter. When we get into gas, oil, anything hydrocarbon-based, it's not going to be conductive enough for a magnetic flow meter. Depending on the fluid, if it coats or scales, it can coat the electrodes and cause errors. Typical applications: water, effluent, pulp and paper mills, mining slurries, brine, liquids for food, sewage, corrosive acids, processed chemicals, engine coolant, the like. The next technology we're going to talk about are positive displacement meters. Positive displacement meters, also known as PD, measure volumes of fluid by counting the filling and discharging of known fixed volumes. A typical positive displacement flow meter includes a chamber that obstructs the flow and a rotating or reciprocating mechanical device that allows fixed volumes of fluid to repeatedly pass. The rate of revolution or reciprocation determines the flow rate. The different types of positive displacement meters: nutating disc, oscillating piston, oval gear, rotating lobe, rotating impeller, reciprocating piston. They're all basically doing the same thing. You're filling the void with fluid. The internal mechanism is rotating. We're counting the rotations of that internal mechanism, and we know the volume of fluid that's trapped in and around that mechanical device. This is a diagram of a rotating impeller meter. So two rotating impellers are driven by the flowing fluid. So starting at the top left, the fluid enters the meter. It goes up against the teeth because this is a liquid. Liquids aren't compressible, so the path of least resistance isn't between the teeth. It's actually to go around the outside of the meter body. So that's what we see as they start to rotate counterclockwise to each other. And then finally, the fluid exits the meter. The little dots in the teeth represent magnets that are embedded in the impeller lobes. There's a sensor on the back side of the meter that detects that magnet as it passes and creates a pulse. Each pulse represents a known volume of liquid that is captured in between the lobes. So each one of these little capsules in between the teeth is what we're measuring. Benefits of PD meters: low to medium initial setup costs. They typically don't require straight run because you're running it in between the teeth. So you're not worried about turbulent or laminar flow. It can be used with very viscous fluids. The higher the better on PD. If you notice the design, there's a tolerance between the teeth and the sidewall. So if you have low viscosity fluids, it can actually slip by the teeth, but the thicker the better. Peanut butter, anything like that, if you can push it through a tube, PD meters are excellent for that. Very high turndown with viscous liquids, up to 1,000 to 1 in the rotating impeller design. They're easy to clean. The cover can be unbolted if you happen to get a plug or an obstruction in there. You take the cover off, you can clean it out, put it back together. The beauty of this is if you do that, you don't have to send the meter out for calibration because of the way it measures. It's just, we're measuring spoons. So we're counting how many spoons just dumped into the bucket. Limitations with positive displacement: they're high pressure drop compared to other technologies because we are obstructing the path to put the gears in. They're very low tolerance to suspension in flow, so you don't want to stop the flow. Applications: chemical and additive injection, adhesives, resins, heavy fuel oil, food ingredients, things such as oil, syrups, chocolate, sweeteners, isopoly blending, ingredients for shampoos, gels, and creams. These are used a lot in batch processes or blending. So if you have part A and part B, like epoxies and such, because of the way they're designed, they can very accurately control the ratio between blends. Dyes, waxes, and lubricating oils. The last technology we're going to talk about is ultrasonic flow meters. A variety of different designs, either clamp on, inline, clamp on. There are two basic technologies. Doppler, it requires suspended solids or air bubbles in the liquid to give a reading. What it does is it pulses into the flow stream, the particles or air bubbles reflect it, and we get a phase shift in the return signal. So it goes out, comes back, but the particles cause a diffraction and a phase shift in the return signal. In transit time, we require clean fluids with no more than 10% solids. This is the basis of our design of ultrasonic flow meters. In transit time, what we're doing is we have a sensor that pulses. It goes downstream and is detected by a downstream sensor. We measure the time it takes to shoot that gap. That distance is fixed. Then we turn around and we reverse direction. So we pulse the downstream sensor to the upstream sensor. With flow in one direction, the time it takes to cross that gap is going to be different because in the downstream side, we'll have a tailwind. In the upstream, we're going to have a headwind. And so we'll have a difference in time in each direction. So that's what we're saying here. This is an example of an inline transit time flow meter. So we're using sound waves to determine the velocity. It has no moving parts. And the transducers, again, we've got a fixed path. We measure the path it takes to go from the upstream sensor to the downstream sensor, and then we reverse direction. Delta T is proportional to the flow velocity. We know what the cross-sectional area is. We're measuring the velocity directly. Volume times cross-sectional area is flow. The trick, delta T is in nanoseconds. These are very high frequency transducers. A little graphic just to kind of illustrate. So with no flow, the time's the same. So as we flow, the downstream is faster than the upstream. Clamp-ons. The features, we can do bidirectional flow. We have no moving parts. Very low cost of ownership. Easy installation. You don't have to section a pipe, mount flanges or taps. And it's non-intrusive. It doesn't have to get into the process in order to make the measurement. No pressure drop because we're not interfering with the flow. Wide range ability with a single unit. This particular unit is adjustable for various line sizes. What you do is you change the distance between the sensors. As the pipe increases in size, you move the downstream sensor farther away. Easy and quick setup. All we need to know is the fluid type, the pipe diameter, the pipe thickness, the material of the pipe. Apply dielectric gel to the sensors and mount them on the pipe. Benefits to ultrasonics. There is no obstruction in the flow path, therefore no pressure drop. No moving parts, so they're very low maintenance. Inline and multi-path have higher accuracy. Multi-path refers to the fact that you've got multiple sensors, not just a single pair. They are used a lot for custody transfer, high accuracy requirements. Can be used in corrosive or slurry fluid flow. Portable models are used for field analysis and diagnosis. Limitations. Clamp-on requires a long straight run, typically 20 to 30 diameters. We don't want turbulent flow. Susceptible to upstream disturbances such as valves, pipe bends. And typically, they're not going to be as accurate. The best you're going to achieve with these is on the order of 0.5% of reading. Inline and multi-beam provide higher accuracy, of course. Typical applications: water, DI water, chemicals, acids, fuels, coolant, low viscosity liquids. Overall, this is kind of the selection guide. So in summary, the meter technologies are across the top and typical applications are top to bottom. So if you have acids, Coriolis, mag meters, DP, or ultrasonic, you're not going to want to use thermal mass. You're not going to want to use Vortex. So this is just kind of an idea. It gives you an idea of what technologies are suitable. And then again, we refer back to the application sheet of these technologies, which one has the best solution depending on accuracy, pricing, and application considerations. That's the end of my presentation. I'll be glad to answer any questions that you have.
Very good. Thank you, Scott. Yeah, we're going to open it up for Q&A, so feel free to throw your questions inside of the chat, or there's a Q&A section where you can just type your question in the module inside of the webinar, and we'll answer those as we come in. And also, just a quick note, we did upload the presentation into the handouts as well as the Vic Myers Associates product line cards, so that you're aware of the other things we represent. First question has already come in, Scott, regarding calibration. How do you calibrate a mag meter?
A magnetic flow meter. So if you're not aware, FTI Flow Technology, we maintain an ISO 17025 accredited calibration lab. We use our gravimetric stand, which is a water tank with different size pipes with it. So we mount the magnetic flow meter to that. We have valves and controls and masters, and so we know the volume of flow as it flows through the magnetic flow meter. We measure the frequency output from the electrodes, and we correlate that to the standard. So inside the electronics, there's a K factor, the meter K factor. And so that's what we're measuring. As we know the cross-sectional area of the tube, we have to measure the K factor, which is, again, pulses per unit volume. And we put a known flow rate through the meter, we measure the K factor, and then the linearizing electronics go over the range of flow to give you a linear output, 4 to 20 or Modbus.
The follow-up question on that is, do you have to take it out of service? Can you calibrate in the field?
We do not do field calibrations. There are companies that do that. What it requires is a calibrated standard, a master meter. Companies that do that, we calibrate master meters for other companies. And so, yeah, a certified calibrated master meter would go in line with your meter to verify the calibration of the meter under question. But as a company, FTI, we do not do field service. We do it in-house.
Okay, we're just standing by here to see if there's any other questions. We'll give everyone a few more moments to see if there's anything that they want to get answered before we sign off here. And I'll just say while we're waiting here, if something comes up after the meeting and you do need some assistance, Scott's information's there on the screen, and you can always reach out to us at Vic Myers, no matter which state you're in. You can just email sales@vicmyers.com and we'll be happy to help you out. I'm going to give it just a few more seconds. It looks like you've done a great job with your very comprehensive overview, Scott. So I think we've been able to answer any questions folks may have. So we'll wrap this up. And if there are any other questions or applications you all would like to discuss, please feel free to reach out. Oop, I've got a hand up. Let's see what we got here. See the hand up, but the question has not dropped into the questions yet. So if you have a question, just type it into the chat or the questions module, and we'll go ahead and get that answered for you. Nope, must have been a false alarm. I think we're all good, Scott,
Okay.
from VMA and FTI Flow Technologies. Thank you all for joining us this week for Tech Tuesday. We really appreciate your time and attendance. If there's anything we can do to help out, please reach out, and everybody stay safe out there. We look forward to seeing you in the field soon. Thanks again for joining.